The first fatal accident in 19 years of nuclear reactor operation in the United States occurred at the Atomic Energy Commission's National Reactor Testing Station in Idaho on January 3rd, 1961. This film, depicting the operations that followed the accident, is a combination of actual and reenacted scenes. It is presented for the purpose of studying and improving the methods and techniques of handling nuclear emergencies. At 9:01 o'clock on the night of January 3rd, 1961, the nation's first fatal accident from nuclear reactor operations occurred at the Atomic Energy Commission's National Reactor Testing Station, known as NRTS, about 40 miles from Idaho Falls, Idaho. The accident occurred in a prototype facility known as the Stationary Low Power Reactor Number 1, and referred to as the SL-1. The SL-1 was built as a result of a request to the AEC in 1955 by the Department of Defense for a small nuclear power plant to supply power and space heat for remote military installations. The reactor, originally designated the Argon Low Power Reactor, or ALPR, was designed by the AEC's Argonne National Laboratory to gross specifications that called for above-ground construction, components that could be transported by cargo aircraft, and a reactor that could operate continuously for 3 years on one fuel loading. The SL-1 core was designed to meet the requirements for extended operation without refueling. The reactor was a direct cycle, natural recirculation boiling water system of 3 million watts gross thermal capacity, designed to produce 200 kilowatts of net electricity and 400 kilowatts of net energy in the form of space heat. It was installed in a cylindrical building 38 feet in diameter and 48 feet high. The building, fabricated of quarter-inch plate steel, was not designed to contain radioactive material in the event of a nuclear accident. This was so because future plants of this type are intended for operation in remote, isolated areas, and the SL-1 itself was not near a populated area. The pressure vessel which holds the fuel was installed in the lower portion center, shielded by local gravel. Most of the plant equipment was installed in the middle portion of the reactor building. On August 11, 1958, the reactor went critical. That is, sustained a controlled chain reaction. And on February 5, 1959, it was turned over to Combustion Engineering Incorporated for operation. It was redesignated SL-1 to conform with military nomenclature. In addition to obtaining operating experience, Combustion assisted the military cadre in training military personnel and was responsible for the certification of reactor operators. Trainees arriving at the SL-1 after an 8-month course at Fort Belvoir, Virginia, were subjected to 3 weeks intensive academic instructions on the SL-1 operation and equipment, and 3 months training as a crew under a shift supervisor. Their training also included a detailed course in health physics. Upon passing rigid written and oral examinations by members of both the military cadre and combustion engineering boards, a trainee was assigned to a regular shift crew. At the time of the accident, the reactor had been operating for over 2 years and had produced 931.5 megawatt days of thermal energy. The reactor was shut down on December 23rd for maintenance and minor modifications. At 4 p.m. on January 3rd, 1961, the day shift was relieved by a three-man crew consisting of a shift supervisor, an operator, and a trainee due to be certified as an operator the following month. Their instructions were to prepare the reactor for eventual startup the next morning, including making the final connections between the control rods and control rod drive motors. According to the log, during the first half of their shift, they had pumped the water down and were reassembling the control rods. Then, at 1 minute after 9, an automatic alarm sounded in Fire Station Number 1, Fire Station Number 2, and the Communication Center of the AEC's Idaho Operations Office. One long and two short strokes indicated the trouble was at SL-1. The Idaho Operations Dispatcher broadcast the alarm over the testing station radio network, informed the Security Division duty officer, and in accordance with pre-planning, requested that a health physicist be dispatched from the materials testing reactor. In less than 10 minutes, the firemen arrived at the SL-1 and found it seemingly deserted. The temperature was 17 degrees below zero. There was no sign of smoke or fire, but low-level radiation was detected. A telephone call to the SL-1 control room brought no response. Both gates to the area were padlocked, as this was the means of perimeter security after hours. A security guard arrived within seconds to unlock the main gate, and the fire engine entered the SL-1 area. The guard unlocked the front door to the administration building, and the firemen entered. It was the quickest access to the reactor building, about 100 feet away. They had a high-range radiation detection instrument and wore respiratory equipment to prevent inhaling contaminated air. There was still no evidence of personnel, fire, or smoke. But 2 feet inside the door, the instrument revealed low radiation levels in the fraction of a Rentgen range. The fire engine was ordered out of the area to Fillmore Boulevard for standby duty. The assistant fire chief reported radiation present at the SL-1, and at 9:20 p.m. notified Combustion Engineering, the operating contractor. He received confirmation that 3 SL-1 personnel were on duty. Combustion Engineering personnel immediately left Idaho Falls to join emergency operations at the SL-1 site. The chief then made another search for the men on duty before the health physicist arrived, again approaching the reactor building by way of the administration and maintenance building. He observed a 25 R/hour reading at the foot of the stairway to the reactor building. There was evidence that 3 men might be in the reactor room. A request was made to NRTS facilities for additional high-range radiation detection instruments, health physicists, and protective clothing. A roadblock was quickly established at the junction of Highway 20 and Fillmore Boulevard for control purposes. At 9:36, 2 health physicists arrived with additional equipment, and one of them accompanied the assistant fire chief into the reactor building. They hoped to locate the missing men quickly. The control room was unoccupied. As they went up the stairway, the indicator swung past 200 R/hour, and they retreated hastily, but not before seeing some wreckage through the reactor operating room doorway. Meanwhile, at the Idaho Operations Office headquarters, 41 miles away in Idaho Falls, a control unit comprising the directors of AEC Health and Safety, Security, Military Reactors, and Public Information Offices was quickly mobilized. The SL-1 accident was declared a Class 1 disaster and immediately broadcast over the NRTS radio network. The Idaho manager assumed responsibility for overall emergency plans and procedures. 3 things had to be done at once: locate and rescue or recover the 3 missing personnel, ascertain the condition of the reactor, and determine how much contamination was being released to the environment. Because of the high radiation problems, protection of all personnel involved was an important consideration in every action taken. In an effort to locate the duty personnel, 2 SL-1 plant supervisors of combustion engineering, one a health physicist and the other an operations man, elected to enter the reactor room. Acting quickly, they located 2 of the men, one still alive, then took dose measurements and returned to the area gate for help. They were joined by 2 more combustion personnel and an AEC health physicist. All 5 returned to the reactor room as a rescue team. They picked up the man who was alive and put him on a stretcher at the head of the stairs. They saw that the second man was dead, and another 4-man team shortly afterward discovered the 3rd man lodged in the ceiling, also dead. The first victim removed was taken almost immediately to an arriving ambulance which had resuscitation equipment. A nurse administered oxygen to the casualty en route to the control point, where an AEC doctor pronounced him dead at 11:14 p.m. Personnel involved in this rescue operation had received exposures up to 27 Rentgens of penetrating radiation. None showed any medical symptoms or required hospitalization. All involved in the rescue operations had to be decontaminated. At the nearby gas-cooled reactor experiment facility and the central facilities dispensary, they vigorously showered and scrubbed in the decontamination rooms. A decontamination problem resulted from the all-out effort to save a life. Since the rescuers couldn't wait for special gloves, their hands required repeated scrubbing. Detergents and potassium permanganate proved to be effective. To monitor for airborne radioactivity, a chartered airplane was in the air at daybreak with an aerial survey analyzer. Very little activity above natural radiation background was detected, except in the immediate vicinity of the SL-1 area. Careful observation showed no damage to the reactor building roof. With all 3 crew members accounted for, there was now time for instituting further safety controls. Organization of recovery teams could proceed more deliberately. Standard procedures for teams working in contaminated areas called for face masks, film badges for measuring radiation, 2 pairs of anti-contamination clothing, 2 pairs of shoe covers, and 2 pairs of gloves. All openings were taped to prevent seepage of contamination. From that time, progressively less contamination and exposure of personnel was experienced. And by the end of the week, The standard operational exposure limit of 3 Rentgens per quarter of penetrating radiation per person was established. Teams were thoroughly briefed to minimize exposure time. 1 minute was set as the time limit in high radiation fields. A health physicist accompanied each team and also acted as a timer. He remained outside high radiation fields to minimize radiation exposure. This was done to conserve available health physicists for the many operations yet to be performed. On the night of January 4th, plans were carefully laid for the recovery of the second casualty. A 6-man military team of volunteers comprised entirely of the victim's fellow cadremen was organized and briefed. It was decided that a blanket would be less unwieldy than a stretcher. The team worked in 2-man relays. The first pair, accompanied by a health physicist, entered the support facilities building and carried the body from the reactor operating floor to the control room. The second pair took over at the reactor control room to bring the victim outside. Then carried him out of the SL-1 area through the perimeter gate. A health physicist measured the direct radiation exposure to the driver. The emergency required other important action that same day, January 4th. Two entries were made into the reactor building to recover the logbook and a neutron detector. This led to later installation of remote reading instruments and audible alarms as a warning against further trouble with the reactor. Also, the reactor building exterior had to be surveyed from the ground for evidence of damage. There was none. Fire and ambulance equipment had to be decontaminated. The field command post, which was to serve for several weeks, had to be firmed up with additional trailers and power equipment. Medical checkups of entry personnel were carried out. Collection of scientific evidence and data went forward simultaneously with the recovery of bodies. The first positive evidence as to the nature of the accident came from a nuclear accident dosimeter recovered from the reactor building. Activation of its gold foil into radioactive gold-198 tended to indicate that an uncontrolled chain reaction had taken place. This was confirmed a day later, when radiochemical analysis of a watch band buckle and pocket lighter screw disclosed copper 64. Only neutron capture could have transmuted naturally occurring gold-197 and copper 63 into into radioactive gold-198 and copper-64. The anticipated spectrum of old fission products was found to be present. Also found were several isotopes of the uranium fuel. Iodine-131 found in sampling of air, soil, sagebrush, and animals collected near the SL-1 verified minimal release of activity from the reactor building. Within 3 hours after each entry into the SL-1 site, film badges were processed to determine the precise exposures received. After the initial entry, no personnel received more than 9 Rentgen's gamma exposure. Special data processing procedures had been initiated by January 4th, involving 2 or more film badges daily for many individuals. Total radiation exposure was tabulated on summary cards. Reports were issued daily by name, date of exposure, and amounts of radiation chargeable to the SL-1 incident. Later, a daily breakdown was issued according to radiation dose and summary of individual accumulated exposures. This information was used in scheduling assignments, planning operations, and in otherwise limiting the activities of individuals. The data also proved to be invaluable as a check on the accuracy and effectiveness of health physics controls. By the morning of January 5th, direct radiation checkpoints covering the entire SL-1 area were being surveyed every 2 hours, and a survey grid was plotted to a radius of 2,000 feet. Calculations were made from readings of direct radiation from the reactor building. As of mid-January, direct radiation levels ranged from 0.002 Rentgens per hour at 2,000 feet to 1.1 Rentgens per hour at 100 feet from the reactor. In contrast, at the top of the reactor, the readings were approximately 1,000 Rentgens per hour. Film badges routinely placed at 1 mile intervals on Highway 20 read less than 10 millirentgens, total dose for a 12-hour period beginning 5 hours before the accident occurred. "19 radio-controlled air sampling stations were started less than an hour after the accident happened. Later, a special network of 11 high-volume constant air monitors was established during January and operated through March 6th. None of the surveys showed any radiological hazard to persons or animals beyond the immediate vicinity of the reactor. On the afternoon of January 5th, an official photographer, accompanied by a health physicist, entered the high radiation zones at the outer edges of the reactor operating floor to obtain needed still pictures. This was repeated on January 8th with another photographer. Working in radiation fields of 500 Rentgens per hour, the 2 photographers were limited to 30 seconds of picture taking each. Using these photographs and other information, careful preparations were made for the recovery of the third body. An Army Radiological Assistance Team from the Dugway Proving Grounds, Utah, offered to assist in the recovery effort for practical experience and training. A quick series of briefings prepared them for their role in a carefully coordinated plan to free and remove the third victim. The third body could not be removed by direct methods. It was situated where radiation levels were most intense, directly above the reactor. Also, there was concern that a heavy shield plug, blown from the reactor vessel head into the ceiling, might fall on the reactor and jar dislodged fuel elements into a second critical mass. The only recourse was to improvise a long mechanical arm that could breach the freight doors at the second-story level of the reactor building, retrieve the body and shield plug as they were dislodged, and lower them to the ground. A hastily fabricated wedge on the boom of a mobile crane was used to pry apart the sliding freight doors. Then a 5 by 20-foot stretcher-like apparatus was fastened to the crane's jib as a catching net. Specially designed and fabricated for this recovery operation, it was carefully maneuvered into the narrow space between the top of the reactor shielding blocks and the monorail of the overhead crane. Here and during subsequent remote control operations, H.K. Ferguson Company, a construction contractor, rendered extensive support. Finally, 5 nights after the accident, 22 volunteers working in relays succeeded in removing the body from the reactor building. On the morning of January 9th, it was transferred from the stretcher to a cask and transported to a shielded facility for decontamination. Medical studies showed that 2 of the men were killed instantly, and the 3rd died of multiple injuries received at the time of the accident. An 8-man medical monitoring team from Los Alamos Scientific Laboratory assisted NRTS physicians in decontamination of the bodies. Gamma-emitting particles embedded by the explosion greatly complicated this work. Considerable success was achieved, however, by washing and scrubbing, including the use of detergents. The use of melting ice proved to be an effective automatic washing technique that minimized radiation exposure time for medical team members. The lining of standard metal caskets and vaults with lead sheeting resulted in final gamma readings at the outer surfaces of the vaults not exceeding 300 milliroentgens per hour generally. This was sufficiently low to permit shipment. On January 13th, the bodies were released to the Department of Defense, which then arranged for burial services in accordance with wishes of the families at private and national cemeteries. This completed phase 1 of the SL-1 operations. Starting with a mock-up of the reactor building at a nearby fire station training tower, phase 2 of the SL-1 accident operations concentrated on determining if the reactor was in fact nuclearly safe. That is, that it would not undergo another chain reaction. Up to this point, emergency operations had been carried out by the AEC. On January 13th, the responsibility for determining the condition of the reactor was turned over to the operating contractor. Proposals from combustion engineering were approved by IDO for remote control viewing of the reactor top head and the interior of the reactor vessel, using both motion picture and television cameras on the end of a cherry picker crane. These remote-controlled operations made it possible to avoid further personnel entries for the next 5 months, or until June 2nd. The mock-up operations also made it possible to perfect techniques for placement and operation of cameras and probes. It was hoped that the pictures not only would affirm that a second nuclear excursion could not occur, but also disclosed what initiated the accident. After several days of rehearsal, the first entry into the reactor building was attempted. Equipment attached to the boom of the crane was maneuvered inside the reactor operating room through the freight doors by personnel operating the crane from a lead-shielded cab. The crane operator was guided by observers who could see directly into the reactor operating floor from a 30-foot tower 200 feet away. With field glasses, every move could be closely spotted for the man on the ground. Thanks to this arrangement and the extensive mock-up training, the equipment was successfully positioned. First films taken of the reactor head area showed that 6 nozzles were open to the atmosphere. Only one appeared to be completely free of obstructions. Films taken looking down through the nozzle openings revealed extensive damage to the visible part of the core and to the control rod shrouds. control rod extensions still protruding up through the nozzles indicated that most of the control rod blades were still in the core region. The central rod blade appeared to be ejected from the core. Closed-circuit television cameras, specially fabricated for radiation resistance, also permitted remote-controlled observations. These were recorded on motion picture film in a canvas-enclosed truck. These lacked definition but had greater flexibility. The operator could be instructed to hold on certain scenes or move more quickly to something else. The core appeared to be expanded radially, and at least one major hole appeared to be discernible. The center of the core was obscured from view. The tops of fuel elements were visible and appeared to be twisted, collapsed, and moved from their original position. All the control rod shrouds appeared to be partly collapsed. The outer shrouds were displaced toward the vessel wall. The central control shroud, number 9, appeared to have been partially ejected upward from the core. Other components appeared to be twisted, collapsed, and displaced. The films obtainable did not prove or disprove that the vessel might be cracked or otherwise damaged. Other photo entries were made with a shielded, remotely controlled miniature camera. It produced still pictures that had to be greatly enlarged, but more completely defined the condition and damage to the core. Contrary to earlier interpretations, the films did not verify that there was water in the vessel. Subsequently, chemical probes containing potassium permanganate crystals confirmed assumptions that the vessel was dry at the time of the measurement. Official conclusions eventually confirmed earlier indications that the reactor was nuclearly safe as long as nothing was done to change its unmoderated condition. The air temperature above the reactor head was 47 degrees Fahrenheit. Inside the vessel, about 7 inches above the core, it was 90 degrees Fahrenheit. And at contact, presumably with debris on top of the core, it was 98 degrees Fahrenheit. First estimates of the radiation field in the reactor room were calculated to be approximately 1,000 R per hour. By late April, the radiation levels had decreased to the 200 R per hour range. Films from a pinhole camera spotted several locations and sources of high gamma radiation activity outside the reactor vessel, presumably from reactor components blown from the core by the force of the explosion. Calculations of the energy needed to cause the observed damage to the ceiling and the reactor indicate that the explosion was sufficient to create an internal pressure of at least 500 psi. From the presence of short-lived yttrium-91M, one of the daughters of strontium-91 found in clothing samples, the total fissions were estimated to be 1.5 times 10 to the 18th, or 1.5 billion fissions. These early calculations showed that the total energy released in the accident was at least 50 megawatt seconds. These levels are equivalent to the energy released by from 2 to 10 pounds of TNT. Beginning shortly after the accident, the SL-1 access road was regularly scanned for contamination tracked out by vehicles leaving the reactor area. Radiological crews cleaned up the hotspots. Wherever possible, vacuum cleaners were used to remove radioactive and other particulate material to the burial ground. In some instances, the activity was leached into the permeable soil with water hoses. In stubborn cases, it was necessary to seal the road surface with resin or neoprene sprays to prevent the spread of contamination. Some valuable lessons were learned early from the SL-1 experience. It is important to have high-range survey instruments that are readily available. These should range to 5,000 R per hour or greater. Special methods must be incorporated into pre-planning for handling highly contaminated and radioactive casualties. A movable lead shield with armholes permits close work with minimum exposures. Also, lead shielding jackets and full-face masks to accommodate eyeglasses. Planning for around-the-clock field operations also pays off. It must be assumed that hundreds of personnel capable of performing a variety of tasks may be needed. For example, photographers were an important requirement. It may be necessary to rely on extensive support from operating and construction contractors, from other AEC installations, and from military organizations. An urgent need for the conservation of health physicists may arise. In the SL-1 operations, more than 80 health physicists were used to advantage during the first week. These were supported by more than 130 other personnel during that time. The SL-1 experience re-emphasized the importance of taking precautions to avoid unnecessary exposures where contamination and high radiation are involved. Although several hundred individuals participated, only 14 of the 100 persons active in the first 24 hours received radiation exposures of 5 or more Rentgens of gamma, and none more than 27 R. Subsequent medical checkups did not disclose any medical symptoms, and no one was hospitalized. The SL-1 accident had little or no adverse effects on the environment outside the immediate reactor area. Life went on as usual in surrounding communities. Repeated surveys and samplings of air, water, soil, vegetation, animals, and milk have revealed very little contamination above background levels. Prompt and factual release of information from the start alleviated public concern. With little public excitement and no sensationalism, a certain recognition was gained of the fact that hazards in the nuclear field, as with those of any other industry, can be dealt with effectively. Regrettable though the SL-1 accident was, out of it has come important information, both to reactor technology and to administrative procedures governing reactor development. Since the SL-1 was not operating at the time of the accident, the Commission's safety program for shutdown maintenance has benefited from the resulting reevaluation. Another constructive aspect was the containment of radioactive particulate matter by a building not designed for that purpose. At no time was there any serious hazard to people and animals, even in the close vicinity of the SL-1 site. This film on phases 1 and 2 of the SL-1 recovery operations was completed as phase 3 sought to determine what destroyed the reactor. Under contract with General Electric Company's Idaho staff, the work of decontamination and taking the reactor apart piece by piece went forward. It was a tediously slow process, extending into the following year. Various potential mechanisms that could have caused the excursion had to be explored. No unknown phenomenon was expected, however. This first fatal accident in 19 years of successful reactor operations activity has been thoroughly investigated from the start by several committees composed of nuclear experts and other scientists. The The investigation will not be complete until continuing studies bring a fuller understanding of what was involved and what can be learned for the advancement of reactor safety technology.